Measure the heights of thousands of adults. Measure the tiny errors a sensor makes. Add up the scores on a long test. Do it enough times, and the same shape keeps appearing. Most values crowd near the middle. As you move away from the center, values grow rarer, smoothly and symmetrically on both sides. The graph looks like a bell. This is the normal distribution, the most important curve in all of statistics. By the end, you'll read any probability of it with confidence. Here, the variable is continuous. It can land on any real value in a range. For a continuous variable, the curve is a probability density function, and probability lives in the area underneath it. The shaded slice between A and B is exactly the probability that the value falls between A and B. Every normal curve is pinned down by just two numbers. The mean mu says where the center sits. The variance, sigma squared, says how spread out it is. And its square root, sigma, is the standard deviation. Its formula looks fierce, but you rarely evaluate it by hand. Notice the heart of it. Minus 1/2 times x minus mu over sigma, all squared. That single piece is what makes the bell symmetric and centered at mu. Let's feel what those two knobs actually do. Start with a bell centered at 0. Turn the mean knob and the whole shape slides sideways. Its width untouched. Move mu right. The bell marches right. Mu is pure position. Slide it back and turn the spread knob instead. A big sigma flattens the bell, wide and low. A small sigma pinches it, narrow and tall. Yet the area underneath always stays exactly 1. Every normal curve hides the same beautiful pattern, measured in steps of sigma out from the mean. It's called the 68, 95, 99.7 rule. Stay within 1 sigma of the mean, one step either way, and you capture about 68% of all the values. Stretch out to 2 sigma, and you've swept up about 95% of everything. Reach 3 sigma, and you've enclosed 99.7%, almost the entire distribution. Beyond 3 sigma, values are genuinely rare. Keep these 3 numbers in your back pocket. They're approximate, but they're perfect for a quick sanity check. If a careful calculation says a value 1 sigma from the mean is somehow unusual, you've made a mistake somewhere. Here's the snag. Every choice of mu and sigma gives a different bell, an endless family of curves. We can't tabulate probabilities for all of them, so we pick one reference bell to rule them all. Set the mean to 0 and the standard deviation to 1. This is the standard normal, and we call its variable z. On this fixed bell, we define one master function, capital Phi of z. It's the area to the left of z, the probability that z is at most z. That's the cumulative distribution function. Two values are worth memorizing. Phi of 1 is about 0.8413, and phi of 2 is about 0.9772. Two properties make phi all you ever need. First, the bell is perfectly symmetric about 0. So the area left of minus z equals the area right of plus z, which means phi of minus z is simply 1 minus phi of z. Second, the complement rule. Since the whole area is 1, the probability z is greater than z is just 1 minus phi of z. Between these two identities, a single left-hand phi answers every question, left tails, right tails, and negatives alike. Now the bridge that connects every normal to that one reference. Take any x, subtract its mean, and divide by its standard deviation. That single recipe is called standardizing. The result is always the standard normal. And z has a lovely plain meaning. It counts how many standard deviations you are from the mean. Watch it in action. If x sits exactly to sigma above the mean, then z is 2. If x is 1 sigma below, z is minus 1. Positive means above the center, negative means below. So any probability about x becomes a probability about z. Standardize each boundary into a z-score, and then just read phi. That's the whole game. Let's make it concrete. X is normal with mean 50 and variance 10 squared, so sigma is 10. We want to probabilities. Part 1. To find the probability x is at most 60, standardize 60. 60 minus 50 is 10. Over sigma 10 gives z equals 1. So the probability is phi of 1, which is about 0.8413, roughly 84%. Part 2. The probability x lands between 40 and 60. Standardize both ends. 40 gives z equals minus 1. 60 gives z equals 1. So we want the area between minus 1 and 1. That's phi of 1 minus phi of minus 1. By symmetry, phi of minus 1 is 1 minus phi of 1, 0.1587. Subtract, and we get 0.686. About 68%, exactly the 1 sigma rule. A second example, this time with a tail. Test scores are normal with mean 100 and standard deviation 15. What's the probability a score is at least 130? Standardize 130. It's 30 above the mean. Over sigma 15. That's z equals 2. We want the upper tail. The area to the right of z equals 2. But phi always gives the area to the left. For a right tail, we take the complement. 1 minus phi of 2. That's 1 minus 0.9772, which is 0.028. A little over 2%, a rare high score. Your turn now. X is normal with mean 500 and standard deviation 100. Find the probability that X is at least 700. Pause the video and try it before I do. Here's the walkthrough. Standardize 700. It's 200 above the mean. Over sigma 100. Z equals 2. Same Z score as before. It's an at list. So a right tail, 1 minus phi of 2. That's 1 minus 0.9772, which is 0.0228. If you got about 2%, you've truly got this. Trap 1, the most common of all. You standardize by dividing by sigma, the standard deviation, never by the variance. If the variance is 25, sigma is 5. Always take the square root first. Trap 2 phi always measures the area to the left. For a greater than probability, take 1 minus phi. Reading phi itself as a right tail is a classic slip. Trap 3. Negative z-scores. Tables often list only positive z. Use symmetry. Phi of minus z is 1 minus phi of z. Mixing up that sign flips your answer entirely. Trap 4. Interval order. For a range, it's phi of the upper bound minus phi of the lower. Do it the other way, and you get a negative number, which can never be a probability. And trap 5. For any continuous variable, the probability of one exact value is 0. Area needs width. That's why less than and less than or equal give the very same answer. Let's lock it all in. The normal is a bell fixed by two numbers. Mu shifts it left or right. Sigma makes it wide or narrow. To find any probability, standardize, subtract mu, divide by sigma, and every bell becomes the one standard normal, z. Then read the area with phi, remembering the area is on the left, using symmetry for negatives and the complement for tails. Identify mu and sigma, standardize, look up phi, and check the answer sits between 0 and 1. Do that, and no normal problem can surprise you.